participants, and the most important was today's speaker, Dr. Sonal Mazumder. So we had our President, Professor V.V. Baswarao. Sir, please, with your kind permission, we can proceed for the session. So kindly give us the proceedings so that we
Please
can
proceed.
start the session.
Please proceed.
Okay. So I just introduce about the Dr. Sonal. Dr. Sonal Mazumder is currently the regulatory reviewer, chemical engineer in the Office of Pharmaceutical Manufacturing and Assessment at the US Food and Drug Administration. Dr. Mazumder has been with the FDA since 2016. During her tenure, she has been actively involved in research involving oral and transdermal drug products. She led the continuous manufacturing group in the research office and supervised several important projects on oral films, transdermal patches, training reviewers, and follows with special focus on quality by design efforts. At the present, Dr. Mazumder conducts scientific review and quality evaluation of the manufacturing process and facilities for application submitted by industries on different generics and RLD drug substances, products, and processes. She also participates in facility inspection as subject matter expert. Prior to FDA, Dr. Mazumder served as an assistant professor in the Department of Chemical Engineering at BITS Pilani for almost more than 3 years. There she established labs and conducted research on nanotechnology in drug delivery and other chemical engineering applications. She received her bachelor's in chemical engineering from West Bengal University of Technology, Heritage Institute of Technology, MTech in nanoscience and technology from Jadavpur University, and a PhD in molecular science and engineering from Virginia Tech. So thank you, Dr. Sonal, for accepting our invitation. And with this, the difficult time, you agreed to deliver an invited talk in this SCHEMCon 2020 to make this event a grand success. So now, please proceed with your presentation. And I'm requesting Mr. Sarkar make her as a presenter. Thank you, Dr. Sonal.
Thank you so much, Dr. Ghosh, for this introduction, and thank you to you and your team for inviting me for this presentation. Whatever time it is always a pleasure to be able to interact with my colleagues, my staff and students in India. And it is about 11 o'clock here, and I know it's just morning there. So probably everybody is geared up with their tea and coffee for this invited talk. So before let me share my screen quickly. Can you see my screen? So before I proceed further with my presentation, I would like to say a few words. So when I was an assistant professor, my students used to always ask me that, Madam, what is our future? What kind of jobs we are going to get as chemical engineers? So, students are always so anxious about what jobs they'll get. So I used to tell them that chemical engineers don't get jobs, they give jobs. So make yourself capable so that you can give jobs. And I think all chemical engineers have that capability because we always work towards sustainable solutions. And that's why I am myself very proud of my students and all the chemical engineers that I've always interacted with, because some way or the other, they have always been a part of sustainable solutions. And to that, this SCHEMCon 2020 has selected sustainable industrial solutions as their key topic. And I thought maybe one of the work that I do or I have been in touch with could be a good talk to deliver and share some knowledge with you all. And that is continuous manufacturing, which is a key to a sustainable manufacturing. So I don't know like how many of you have heard about this. Probably you have heard. It's not anything new. but it is something that has come into picture very recently, and there has been a lot of pressure on the industries to move from batch or typical batch manufacturing to continuous manufacturing. Now, during this presentation, I would like to emphasize more on pharmaceutical examples, because that's what has been my experience and expertise with for past few years. And so yeah, continuous manufacturing is applicable in steel industries and oil industries from decades or generations, but it has been relatively new or novel in pharmaceutical industries because of its inherent challenges. But today I want to make the talk in such a way that it's more fundamental and more applicable to students from the chemical engineering point of view. And I hope that I'll be able to share some knowledge and give you some good understanding of this process. So to begin with, I hope I'm audible and my slides are visible. Um, so yeah, to begin with, I would just pick up an example from your very typical chemical engineering book, that is a batch operation. And probably all of you know what is a batch operation. So it is just, as you can see, the images of batch reactors. So when we talk about batch operation, it is a closed system. That is, you have a reactor, in this case, a batch reactor, where you have some materials that you charge in the reactor at a certain time point. And then there is a reaction which goes on. And during the reaction process, the conditions keep on changing with respect to time. And then after the process is complete, the materials are discharged from the reactor. So this is the example of typical batch operation, and probably all of you are aware of it. Um, Please note that the conditions change over time. So, um, so what is the key issue here? The key issue is the effect of time, that is the conversion versus the duration trade-offs. So if you see this graph, which is conversion versus time, you see in case of a batch reaction, so what happens? Like you have a specific product demand at a certain fixed time, right? So in order to achieve a higher conversion, you need to run it for a longer time. And in order to run it for a longer time, you need a larger batch or a larger batch size, and therefore a larger equipment in several cases, right? So this is how the batch operation or the batch processes operate. So let me give you an example of something which is called a batch processing train. So if you see, like let's say in a process, and I will pick up again some examples from your chemical engineering equipments or the batch units that you have been through. So let us pick up a reactor, a crystallizer, a centrifuge, and a dryer, which are been in series and one after the other, and you are having a batch operation going through that train. So this is called a batch processing train. Now, if you see these bars, the red, the blues, and the purple bars, these are the time that is taken by each of these batch units. So this graph has in its horizontal axis is the time, and the vertical axis is all the batch units. So the bars in the graph are the time that is taken by individual batch units to complete its own process. And the arrows, the vertical arrows connects from one batch unit to the other, and the time that is between the completion of one batch to the other is called a cycle time. Now, if you see minutely, then if the cycle time is less, that's how we can have more product. Like if you want to have better product, you need to have lesser cycle time between one batch process to the other batch process. But what happens that when you go from one batch unit to the other, the former batch unit is actually in an idle state. So as for example, just to simplify it, like you have a reactor, so your reaction is done in a reactor, then it goes to the crystallizer, then it goes to the centrifuge, and then it goes to a dryer. In this case, if you see, the dryer actually has a longer processing time. And when the drying operation is going on, the other batch units are just sitting idle, right? And therefore, it is underutilization of time and also equipment. So you are in like involving a lot of different equipments, but you are also consuming a huge amount of time. So this is to give you an example that what happens in a batch process. So there's a lot of idle time. Well, with that, even though the timing is an issue, and then you have to have a larger equipment if you need more product, or if you are underutilizing. But batch processing has certain advantages, right? And a lot of industries are still, they are so adamant in using the batch processing because of the extreme flexibility that it offers. Like, first of all, it's like cooking. You know your vessel, you know your recipe, and you are just cooking, and you can change from one vessel to the other, and it's very easy. Multi-purpose equipment, as for example, you can use one equipment for multiple purpose and for multiple products. It's adaptable, and easily you can change the recipe. So as for example, like, you can just simply use any kind of recipe and use that in your batch system. And in order to do all of this, you just need a very limited process understanding. So as long as you're confident about using or doing what you're doing in your system, it should be pretty simple for you to just charge any material, get the process done, and then discharge and get the product what you want. And because these are very discrete in nature, so it's much easier to track of lots. Lots here means that a certain batch size which has same quality or same properties. So it's very easy to discretize or to get discrete to track the discrete batch sizes. So these are some of the advantages for which it is still very, very popular. Now, the disadvantages to what I've already described before is that it is an extremely dynamic process. So it is affected by human or environmental factors. So as for example, since it's a closed system and you are just, once you charge in the materials and the reaction starts, you cannot do any kind of modification. And if any kind of error happens, there is very less probability of controlling it. And then unless the batch is finished or completed, there is nothing much you can do about it. Then, as I already explained with the batch processing train, it has a very low equipment utilization or poor capital utilization. So a lot of times, unnecessarily, you need a large equipment. Of course, the clean out and changeovers consume time and materials. And if you want to scale up, again, scale up is a big challenge. So if you want to scale up from a small batch to a larger or commercial manufacturing batch, it requires a lot of recipe modification. It's not as simple as just linearly you are increasing everything and it just works out. So these are some of the challenges faced in batch processing. So is there a need for equipment change? So again, as I said, that I will probably pick up examples from the pharmaceutical industry. So what it was in 1920s, the equipments are still used now. Maybe there are some little minor here and there, some updates, but mostly like they are been utilized now. But if you look into how the audio industries have changed in 1920s, there was a gramophone, but nowadays music, we hear it through our smartphones. So see the huge change or development in technology compared to the industries where they are still extremely into using the obsolete equipments or the processes to keep running the manufacturing. So in 2011, in the American Association of Pharmaceutical Sciences, they said that right now, manufacturing experts from 1950s would easily recognize or whatever they'll see and just understand the process which is today. So in 25 years, all this process is going to be obsolete. So it is extremely important to shift from batch to continuous process, because that will really change how things are done and will make production less polluting, more flexible and local. And in your words, or in the words of SChemCon, more sustainable. So it is important that we see that what is a continuous process and how it is going to help us in having more sustainable manufacturing, especially in terms of the pharmaceutical industries. So what is a continuous operation? Compared to a batch operation, a continuous operation is an open flow system. So there is a continuous input and the operation is happening, and there is a continuous output, and this is happening continuously. So as for example, I'll give you an example of the same batch reactor. So instead of just having input of materials and then an operation and then output, we are continuously, let's say we are continuously feeding the materials in the batch reactor and continuously taking it out. And there is a continuous mixing of all the materials inside the batch reactor. And we kind of control the input and the output by the level of the level of the fluid inside the batch reactor. And this is something probably you have seen in your like reaction engineering or books, chemical engineering books. So it's pretty straightforward, but everything is happening here continuously. And another example could be a just simple tubular or plug flow reactor, where again, you have a material which is fed from one side and you have the output, which is then taken out from the other side. And it is an open system, everything happens continuously. Now, the most important thing that you have to keep in mind in case of a continuous operation is the state of control. That is, when the operation is going on, you have to see the variations of the properties are within the acceptable limits. So because it is going on continuously, and if there is an error or if there is a deviation, then the product that you get is definitely of no use. So you have to be extremely, extremely careful about maintaining the state of control. So I'll give you an example, or I'll give you a little bit of idea about what is a state of control. So before that, a little bit about the continuous processing advantages. So high equipment utilization. So you don't need a lot of equipments to actually manufacture a lot of product, right? So if you want 5 milligrams or 5 kg or 500 kgs, you can still use the same equipment and run continuously and still get the same product. So therefore, it requires smaller equipment footprint, and scale up challenges are reduced because most of the time the scale up means like you just scale up to get more product. So that is much reduced because often you don't need that. Reduced material inventory, variability in output is reduced, and simplified online measurement and automation. You can also improve temperature control and enhance safety, and also improve micromixing control. So all of because of the continuous process, the nature, we can really control all of these and we can have a much better product, a much cleaner, safer, controlled product with a good quality, and of course with much lesser cost and lesser footprint. However, it has certain disadvantages. So as you will see in my next subsequent slides, that it definitely requires a much detailed process understanding, because you have to do a lot of different controls, less flexibility in accommodating different products. So again, because this is a continuous system, it's not your cooking vessel, so you can't just use it for all different kinds of products. And it requires a good knowledge and good understanding of in-process control. I'll just go a little bit, I'll touch upon this topic, I'll not go into in depth, but nowadays what industries are doing is that sometimes it's a little challenging. You just can't have a batch system for years and just suddenly move into a continuous system. So they have moved into something called hybrid. So a certain part of your manufacturing process is more of batch in nature, and then the certain part is more of a continuous in nature. And they have tried to kind of made a hybrid of that. So as for example, if you see an example here, you have a continuous start tank reactors where there are 3 reactors in continuously they are being fed and discharged and from one to another. And then whatever product comes out of the last unit goes into a storage, intermediate storage. And then this from the storage, it goes into a batch distillation column. Now, in order to even maintain a hybrid system, it has to be very important that the batch, whatever is the production rate from the batch and the continuous, they must match. Otherwise, there will be difficulty in running the whole manufacturing. So these are some of the very common processes that industries are using nowadays. So to go a little bit in depth about the state of control. So what does a state of control means? Does it mean constant flows and properties? No, it doesn't mean constant flows and properties. It means that, let's say any property you pick up, let's say a mass flow rate, okay? So you have a target mass flow rate. Let's say you have a target mass flow rate of 50, or like any kind of properties that you are thinking about. it should be within the acceptable limits. So you do a risk assessment, you find out what are the upper limits or lower limits, and you must control your system or process in such a way that it doesn't go beyond that limit. That is what is called a state of control, because no process is without any disturbance. All processes undergo some kind of random disturbances. So in state of control means the variations would be in acceptable limits. So if you see this chart, you see within the smaller circle in the center is the target. So that is your target variable or the target parameter. And then outside in the yellow region is the NOC, which is normal operating condition. Now beyond that, if your property varies, it becomes upset. And when it is in the upset region, then your product is called a non-conforming material or non-conforming product. So that means the process is not under control. And if it goes beyond that, then it is ESD, which means emergency shutdown. So emergency shutdown, you have just no other way. You have to just shut down your process. So we always try to stay in state of control and see, or our whole process understanding is based on how we can detect any kind of upset, or how we can make sure that our variables or the properties are within the state of control. That is what is the key in continuous manufacturing. So here is again another thing that you have seen again in your process control books. So let's say you have an API content. Like if you see this graph, there's an API content. API is active pharmaceutical ingredient, or in very simplified, it is a drug substance. So with time, we are trying to track what is its composition. Now the green straight line shows its target value, and of course the black line up and down, it's the deviation that is going through, and the yellow dotted lines are the lower and the upper acceptable limits. Now you see that there's a, can we, if there's a deviation, can we correct that deviation? Yes, we can correct that deviation. Now this is in case of a random disturbances. So as for example, if you can see, like we can use a feedback loop, a feedback control strategy in order to correct such kind of deviations. So if there is a disturbance in the operation, there's a controlled output. So what happens, a feedback loop utilizes the target value and the output and deducts it and finds the error and feeds the error to the computation or the control logic in this case. And the control logic actually helps in the control action, and they make some corrections to the manipulated variable, and which then comes back, or it's then comes back to the operation as the control variable. So this process is going on. So in a continuous manufacturing, what you need is a feedback loop so that it can detect the error, it can transform the error into a control action and give you a corrected variable to go through the process again. So that way, any kind of random disturbances you can detect and you can correct also. So that is one kind of state of how to achieve the state of control. But not always you only have random disturbances. And if there are random disturbances, your feedback loop or the process control feedback loop is capable of detecting that or correcting that. But if you have non-random deviations, that has some different ways of handling. So what are the non-random events or deviations, such as something from the equipment or the sensor or any kind of controller malfunction? Let's say the feed property or the environmental condition has changed. So all of these changes, the control logic cannot handle, and they require spatial mitigation or spatial, spatial kind of treatment to mitigate those kinds of deviations. And if we don't mitigate or this kind of deviations occurs, what we will get is non-conforming products, and these products are of no use. So we have to make sure that these deviations are not achieved, or even if it is there, we know how to correct them. There lies the challenge of continuous manufacturing, to be able to detect this deviation and to able to kind of divert or make sure that the non-conforming materials of the products are not a part of your product, list. Um, so how As for example, again, the same graph, you see there's an upset boundary and there has been deviation from the acceptable upper limit, and it has actually crossed the upset boundary and gone further beyond that. So what do we do then? So we have few methods, as it like number one is online measurement of critical variables. So if there are critical variables, you have to measure them online, and you can determine the deviation and see if it is statistically significant. And once it is detected, of course, you have to diagnose that and mitigate that. Now, I will touch upon just 2 points so that I don't run out of time before I finish. That how do we do such mitigation? Like how do we detect those deviations and how do we mitigate them? Number one is residence time distribution. Again, I will not go into details because probably a lot of you have already known. So simply, it is how much a fluid particle actually resides inside a system. Like let's say you have in this case, you have a blender, a continuous blender. So you have a drug substance, you have an excipient, they flow into a continuous mixer or a blender in this case, and they flow out. So let's say if you think of a fluid particle which is flowing through the system throughout the length of the blender, then let's the particle that it spends the time inside the blender is its residence time. Now, when it spends in like whenever it is inside the blender, it undergoes a lot of different phenomena, such as it collides with each other, then it collides axially, radially. There can be frictional forces. Even the blender or the mixer, which has the the impeller, that has a certain RPM, so it can collide with that, and all of this can vary the residence time distribution. And therefore, if you see the graph, you get a distribution for like if you kind of divide the whole length of time into number of beans and try to track the particle, try to track the time, the residence time of the particle, you'll find a distribution. That is the main concept of the residence time distribution. And this is highly required, or this is highly used in order to understand the deviations, the distribution of a particle inside a continuous system. This is very, very important. And just to give you an idea that if it is an ideal plug flow in the pipe, where there is no variation in the velocity, it's a constant velocity. Let's say we assume that there is no mixing, there is no wall friction, then there is no distribution of the residence time. You will just see a spike. When you see at the frequency versus time graph, you will just see a spike because it is simply the time is given by the length by the velocity. But if you see a real flow in the pipe, where there is velocity distribution, there are different frictional forces or any kind of mixing in the axial direction, you will see, as you see in the graph, that it will start with a spike, but as it moves through the pipe, the variation, you can see the variation in the residence times distribution. And often such experiments are done with dye, a tracer element, and they are just fed into the system, and then the composition or the concentration is tracked throughout the length of the system. So this is one method, and of course there's a lot of things to know about the residence time distribution and how it functions in a continuous system, but I will not go into that. This is just to give you an idea. The next thing is the integration of PAT into the continuous manufacturing or the CM process. What is PAT? PAT are online tools, process analytical tools. So these are analytical tools like you use, like the UV-Vis, the SAM, TAME, the spectrophotometer, or anything, any kind of analytical tool, thermal, spectrophotometry, anything that is being used to detect any kind of properties which is happening throughout this line. So in a continuous manufacturing system, we call the whole thing as a line because it happens in a line. So I will give you an example of tablet manufacturing system here. So if you see at the top, you have feeders, layer 3 feeders. One is the API, which is again the drug substance. Then you have the excipient, which is the polymer or the other kinds of materials which you need to make the product. And then you have a lubricant, which helps to kind of to help the flow of the materials. And then it goes into a mixer or a blender. And from there, it goes into a hopper. And then they go to a roller compactor, like it compacts whatever the mixed powder that they got. And from there, it goes to a mill, which then breaks into smaller sizes, and then it goes into a hopper and finally into a tablet press, where the tablet making happens. So um, first we have to understand that where are the places that error might cause or deviation might cause, because this is everything is happening in one line. And so as for example, it's very important to know the flow rates of all these three are in sequence so that it doesn't deviate and it doesn't disturb whatever is going into the mixer. Now, whatever is coming out of the mixer, we need to measure the concentration on the uniformity, especially the drug uniformity there. So we use a NIR or Raman spectrophotometer there. Then we measure density and uniformity again when it comes out of the roller compactor. Then PSD is the particle size distribution because they break into smaller particles when it goes through the mill. So we have to measure that. And then once it comes out of the press, like a tablet press, and we get the tablet, we need to measure the weight, hardness, assay, etc. So there are different properties that we need to measure to make sure that all throughout the process, whatever we are getting is what we desire or within the acceptable limits. Any deviation we see, any offset or upset we see, we have to immediately decide on how to mitigate that right away so that it doesn't affect the final product quality. So what if uncorrectable upset is detected? So let's say you have a line and you see there's some upset and you can't correct it. What you do? So you do three things. One is either you reject any material at the end of the line. So I'll actually go to the last because I think I'm over time. So I'll just go to the last slide. So this is my last slide. So there's the first thing that you do is when you see that there has been some upset and something has been beyond the acceptable limits, the one thing you can do is you reject at the end, like you reject that batch from the end, any of the non-conforming material. You can also do a rejection intermediate. Let's say you see a deviation here, you can simply reject that batch from here or that amount from here, and you can keep doing the process. Same here, you can also reject something from, so they can do intermediate. Or another option can be you can slow down or you can manipulate with the production rate at the downstream to make sure the upstream can catch up. So there are a few things that you can manipulate throughout the process, but for that you need a very thorough understanding of the process, the deviations and mitigations that you can do. So I think with that, I would like to summarize that I gave you some idea about what is a continuous system, how it is different from a batch and hybrid system, are the different advantages and limitations, what is a state of control, why is it important to keep the continuous system in the state of control and how we can sustain that, and how we can detect and measure deviations and mitigate them by using RTD and also some online pack tools. And with that, I'm going to end. And thank you again so much. It would have been much better if it was more like an interaction with a hall of people. But I think the new normal is what we're getting used to. Again, thank you so much, the organizing team, and to all of you who had been in this session and listening to me. So if you have any questions.
Thank you very much. So now I'm opening the session to for question answer. If you have any query, please put forward to Dr. Sonal. So I think President sir, if you want to say something.
Yeah, it is a very knowledgeable session, and she has talked about the batch processes and continuous processes, and what is the necessity of RTDs studies, and how they will help in controlling the process, and that's good. And I thank Sonali, Dr. Sonali, for delivering the lecture. Thank you.
Sonal Mazumder.
Sonal Mazumdar, yeah.
Yeah,
It's
thank you
good.
so much.
Yeah, thank you.
Yeah.
Yeah. Yeah, please ask the students to interact with her. It seems she's having
Any query? If anybody having any participants can ask a question, you unmute yourself and you can forward your query.
and let them type in chat box. That would be better.
Yeah, I think
Uh,
Yes, if you you can write also chat box to get the answer if you think so. And otherwise, we'll conclude this session. And again, I convey my sincere thanks to Dr. Sonal for in this odd time you are delivering the lectures from USA. So I must say the thanks from the organizer SCMCon 2020, and hope that near future also will invite and you will come forward to deliver different topics, most importantly in that the drug regulatory system, so people are interested to listen. So hope if we invite you in due time you will be getting permission from your
yeah,
authority to deliver
yes,
the lecture on your this the subject the drug delivery. So this time actually, sir, due to shortage of times, he could not get permission from the FDA
okay.
to give the lecture on that subject. So see,
I am also interested to arrange a lecture for her because I am the dean faculty of pharmacy in Usmania University.
system.
So we have almost 25 pharmaceutical institutions, affiliated institutions in OU region, Usmania University region. So your knowledge will be benefit to the all our no faculty as well as students. So if I request and
absolutely.
please, okay, thank you.
Yes, absolutely. That would be great, and I would be definitely interested. It's just as I mentioned to Dr. Ghosh this time also that
Yeah,
usually FDA takes about 30 days to do the paper processing for any kind of permission because you know this agency is extremely secretive about what we present outside or not. So we have to go through a certain process before they say yes to it.
yeah,
So just make sure that you give me at least a month time
month.
beforehand.
Okay, yeah,
Yeah, so that will be much, then I can be more comfortable in discussing some of the really core regulatory issues or challenges or things related to pharmaceutical industries. Yeah,
okay, that's fine. Thank you,
sure.
Abhijit. Let us conclude, or I think Praveen sir is there. Praveen, sir, Praveen sir. Okay, Abhijit, please conclude.
We can't hear you, I think.
Yeah, please unmute yourself. Abhijit, you are not audible. Hello. I think there is some problem.
yes, now
Yeah.
so now audible.
Yes. Yes. Yes.
Okay, so thank you very much. So we are ending the session, and
Okay,
we'll hope that we'll again meet for
sure.
ICG different activities. Thank you, Dr. Shonal.
Thank you, everyone. Thank you so much.